G'day nerds. So let's have a look at the ideal gas laws. In fact, the whole collection of laws we call the gas laws. So by the end of this, I want you to be able to apply the gas laws to a calculation, as well as be able to use the gas laws to explain what's going on with changes in a gas, changes in a volume, pressure, etc. Right here we have your vocabulary. If I get you to pause the video, write this down, and just keep this in the back of your mind as we move through the video. Alright, so when we talk about an ideal gas, and now we've got some excellent lawn mowing happening behind us, when we talk about an ideal gas, there are four variables that we're really interested in. First, we have the pressure, and this is the amount of particles that are hitting the walls of the container or the push against the edge. So how often, basically, they're hitting against the edge of the container, and we measure this in atmospheres. We want to talk about the volumes, which is the size of the container. We measure this in liters. We also want to talk about the moles, or the amount of gas particles. And we measure that in moles, by the way. We want to talk about temperature as well, which is the kinetic energy, or how fast the particles are moving. That's what temperature actually is, how fast the particles are moving. And we measure that in Kelvin, because it's a good absolute measure. So let's talk about Boyles Law first, where we keep temperature and moles constant. The first thing we need to know is, so we're talking about pressure and volume here, is that pressure and volume are inversely proportional. In other words, as the volume halves, pressure doubles. And we can see this in this piston just over here. Or, as volume doubles, the pressure halves. So as we increase the volume, the amount of times that those particles are hitting the sides of the walls decrease. And we get this equation here, which is P1 V1 equals P2 V2. So what that means is, if we need to rearrange it, if we change the volume, if we change the pressure, we want to see what the volume is, we could bring P2 over here, divide it by that, and that'll help us work out what the new volume is going to be. Then we've got Charles' law. Now, Charles' law talks about keeping pressure and moles constant. So we're looking at temperature and volume. So volume and temperature are proportional, which means as the temperature doubles, the volume doubles. So if a container is allowed to expand, as we increase the temperature, the volume will also expand. Or, as the temperature halves, the volume will halve. And we see this with the equation V1 equals T1, V1 divided by T1 equals V2 divided by T2. And then we come to Advocators Law. So in this one, we're keeping pressure and temperature constant. In other words, this law gets us that equal volumes of a gas at the same temperature and pressure will have the same number of molecules. Therefore, volume is proportional to N. So, as N doubles, or moles doubles, the volume will double. And we see this with the equation V1 over N1 equals V2 over N2. It doesn't say the 2's are the ones there on the ends, but it should. So basically, any gas you want at 0 degrees Celsius or 273 degrees Kelvin will all make up, and at 1 atmosphere, will all make up 22.4 liters, regardless of its mass. So the number of molecules are what determines the size or the volume at set pressures and temperatures. And this brings us to the ideal gas law. This is useful not for when we want to measure a change, but more when we want to work out the composition of all four variables if we've got a few. And this one actually matches up with, this is a culmination of our previous gas laws. And the ideal gas law is PV equals nRT. Now, R is the real gas constant. It's a number which just makes it so that all of our calculations make sense in the real world. And R in this case equals 0.0821 liters times atmosphere per moles at Kelvin. Now, that changes depending on what units you're using for gases, because there are various ones, but here we've used what we call the absolute measures. So let's have a look at a question. How many moles will a 1250 milliliter gas flask hold at 35 degrees Celsius at 1 atmosphere? And R equals 0.0821. First thing we need to do is convert the temperature. So 35 degrees Celsius goes to 308 Kelvin. Then we apply our PV equals nRT. We rearrange it to get the moles on one side. So it becomes N equals PV divided by RT, which gives us 1 times 1.250, because we've read liters, divided by 0.821 times 308, which then becomes 1.250 divided by 25.2868, which becomes, when we apply scientific notation and two significant figures due to the 35 degrees up here, 4.9 times 10 to the minus 2 moles. I hope that made a lot of sense. If it didn't, if you have any questions, put them in the comments below. We'll get to you as quick as we can. Thanks for watching. Bye now.